Last time we ended on the topic of polynomials of matrices. So when we think of a polynomial, we usually think of something like this. P of x is equal to a sub 0 plus a sub 1x and so on. Where these AIs, depending on the field you're working over, is either in the complex numbers or real numbers. But here I'm just saying, let's assume they're in the complex numbers. So they're just some fixed numbers here, and the powers on the x's are 0 or bigger, and they're integers. So here's an example of a polynomial, and what we're going to do is, instead of using x, we're going to replace it with a square matrix. Here we have an n by n square matrix. So we could have the polynomial, so P of a is equal to a cubed minus 2a plus 5i. So wherever we had an x, we substituted it with an a, and if we didn't have an x, we put the identity matrix there, and the identity matrix needs to be the same size as a. So this is a polynomial of the matrix A. And we also talked about something involving e to the x. Remember that e to the x can be written as a polynomial, like this. And we can also define a matrix exponential here. So e to the a is going to look almost identical to this. Wherever I have an x, I put an a, and wherever I have a constant, I put an I. So just like we have the summation notation here for e to the x, we can have summation notation for e to the a. So let's look at a problem. Suppose A is the matrix 5, 6, negative 2, negative 2. And I want to find these two polynomials, 3a squared minus 2a plus I, and e to the a. So what I need to do is I need to square a for this first one, multiply it by 3, and then subtract 2 times this matrix, and then add an I. So this isn't that hard to calculate. We could use a calculator online, or we can do it by hand. I'm going to do it by hand. But what I'm going to do is I'm going to take advantage of the fact that this matrix is diagonalizable. And in a previous video, we found the matrix D that goes with this matrix A. We said that the diagonal matrix is 2, 0, 0, 1, and we found that the matrix X is actually its inverse, and that matrix is negative 2, negative 3, 1, 2. So calculating a to a particular power, at least for the case of this matrix, isn't that hard. But if the matrix was bigger, like it was a 3 by 3 or 5 by 5, 10 by 10, if I want to raise a matrix to a power, it might take a lot of time to compute, especially if it's a big matrix. And if you're using a computer, like a calculator, to do this on the computer, if it's a big matrix, it might take a lot of time. It really depends on the matrix. But we're going to find a quick way to do it. And notice that if I have a diagonal matrix D, so it looks something like this. If I raise this matrix to a power R, then all I have to do is raise the diagonal entries to the power R. So that is a lot quicker than raising the full matrix A to that power. And then after I raise it to the power R, if I wanted to find a to the power R, I would just take this and multiply it by the matrix X, and then the matrix X inverse. So that's what I'm going to do for the first problem. I want to find 3a squared minus 2a plus I. So remember that a squared is x dx inverse times x dx inverse. Here I just wrote it 2 times. These cancel and I get x d squared x inverse. So using that, this is 3x d squared x inverse minus 2x d x inverse plus I. I'm going to bring these constants in, so I get x 3d squared x inverse minus x 2d x inverse plus I. And now I'm going to factor the x out of these two. I'm going to factor it in the front and take the x inverse out in the back. So I get x 3d squared minus 2d x inverse plus I. Okay, so what can I do from here? Well, we know that A is given by this. So I'm going to take this matrix 2, 0, 0, 1, and I'm going to use that to figure out this piece. So 3d squared minus 2d is 3, 2, 0, 0, 1 squared minus 2, 2, 0, 0, 1, which gives us, well, notice that I can bring all of this into one matrix. So this is 3, 2 squared minus 2 times 2, 0, 0, 3, 1 squared minus 2 times 1, which is, well, this is 12 minus 4, that's 8, 0, 0, this is 3 minus 2, which is 1. So I figured out this piece right here, and now I can just plug it in, and let's see what we get. Lasso this up, put it up here, and we said that the matrix A was -2, -3, 1, 2, -2, -3, 1, 2, and then we're going to add the 2 by 2 identity matrix here. Okay, let's multiply these two together first. This just multiplies the first row by 8, so we get -16, -24, leaves the bottom row alone. And now let's multiply these two together. So we get -2 times a -16, that's 32 plus 3, right? Let's just make sure I did everything right. So 32, oh, that's a -3, sorry. -3. And then this is 48 minus 6. This is -16 plus 2. And then a -24 plus 4. So we're left with 30, because this is 29 plus 1. This is 42. This is -14. And then this is -20 plus 1, -19. So this is the solution. Let's copy this. And let's erase all of this stuff. This is the solution to our problem. Okay, so we're just going to say equals, edit, paste, so we get this matrix. Okay, great. So let's use this to try to figure out each of the A. So what we did, let's try to figure out this one here. Okay, I'm going to erase this. So each of the A, we said, is equal to I is equal to 1, the summation from 1, actually I is equal to 0 to infinity of 1 over I factorial times the identity matrix A to the I, which we can write in an expanded form. This is identity plus 1 over 1 factorial A 1 over 2 factorial a squared, and so on. So this is going to be equal to, if we use the same idea as the last problem, the identity matrix plus, or we're going to have an x, 1 over 1 factorial d plus 1 over 2 factorial d squared plus dot 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 dot. So 1 over 3 factorial d cubed, and then an x inverse on the back. We know that the matrix D is equal to 2, 0, 0, 1. So I'm actually just going to write this. So this is going to be 1 over 1 factorial 2 plus 1 over 2 factorial 2 squared plus 1 over 3 factorial 2 cubed plus dot 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 0, 0, 1 over 1 factorial 1 plus 1 over 2 factorial 1 squared, and so on. Do you see what I'm doing here? I am taking the matrix D, and notice that this is a scalar that can go in, and so you see that 1 over 1 factorial, the times D would be 1 over 1 factorial 2, 0, 0, 1 over 1 factorial 1, and then this one would be 1 over 2 factorial 2 squared, 1 over 2 factorial 1 squared, and since we're adding them, we just put it all on the same line. And then we put the x inverse on the back. And so we could say that this is equal to the identity plus x times, well, this is actually the sum. I is equal to 1 to the infinity of 1 over I factorial 2 to the I, right? But the only difference is we're starting at 1, and 0, 0, I is equal to 1 to the infinity of 1 over I factorial 1 to the I, x inverse. So the difference here, you can see that we start at 1 instead of 0, but then what is this actually equal to? So this is e to the 2 subtract 1, because we don't include that first element because we started at 1. Originally, e to the 2 is 1 plus all of this stuff. So you can see if I wanted to solve for this, I just move the 1 back. So we're left with the identity plus x times e squared minus 1, 0, 0, and this is e to the 1 minus 1, x inverse. So we can just say that this is 1, 0, 0, 1 plus, well, x was -2, -3, 1, 2 times e2 minus 1, 0, 0, e minus 1, -2, -3, 1, 2. And if we want to finish this calculation, we can. We just need to multiply these matrices. And I think you can do that, figure it out, but you can see that you can calculate this just by multiplying this out, and we could get the answer. So I'm going to stop here, but as an exercise, you can finish this multiplication and see what you get as e raised to the a. And you could also plug it into maybe some computer software like Desmos or Symbolab, I think that's what you call it, .com, and I'm sure that they could calculate this for you. You can see if you get the same answer. So I'm going to leave it here. All right, the next thing, actually we can just write a little bit further down. The next thing I want to talk about is writing a vector in terms of subspaces of a vector space, like if we have a direct sum. So if V is equal to W plus T, where W and T are subspaces of V, and remember that for a direct sum, the intersection of W and T is equal to 0. We know that V, lowercase v, if it's a vector inside our vector space, capital V, then V can be written as W plus T, and this is a unique way to write it, where W belongs to capital W and lowercase t belongs to capital T. We touched on this when we first introduced direct sums. That was back when we talked about orthogonal subspaces. We said things like V is equal to, if we had a vector space V and W was a subspace in V, then W plus its orthogonal complement was equal to V. We did stuff like this. I want to bring this in to eigenvalues and eigenvectors. So we mentioned that if we have a matrix A that's n by n, and we have eigenvalues, so the characteristic polynomial looks something like this. Then we have k distinct eigenvalues. And we have k distinct eigenspaces associated to those eigenvalues. We also said that each one of these eigenspaces is actually a subspace of Cn. And we said that E lambda I, if we intersected with E lambda j, we are left with just the 0 vector. We can talk about the direct sum of such eigenspaces. So we can say E lambda 1 plus E lambda 2. We could do E lambda 1 with E lambda 5 plus E lambda 7. Or we could add them all. So we could say E lambda 1 plus E lambda 2, and so on. My question is, when is this, because this is going to be a subspace of Cn, because each one of them are their subspaces, and their intersection is just the 0 vector, but when is this actually equal to Cn? Think about that for a second. When would the sum, the direct sum of all these eigenspaces be equal to Cn? Well, remember that Cn has a basis with n vectors. Each one of these eigenspaces, they have a basis. Let's call it B lambda 1, basis B lambda 2, and so on. And every vector, we saw that any vector in E lambda 1, including a basis vector, is linearly independent from any vector in these other eigenspaces, including the basis vectors. So if we take the union, so let's do it in red, let's let B be the union of all these basis vectors. Well, if we take the union of all these basis vectors, if we have n linearly independent vectors, then that would imply that this sum, let's call this sum W, W is equal to Cn. And the reason for that is, well, there's n linearly independent vectors in this basis. It's a subspace. And remember that if you have the same number of vectors in the basis of W as in the basis of Cn, and they're linearly independent, that would imply they span, and that would be a basis for Cn. So these would be, because they're subspaces of Cn, we would have a basis for Cn. Now if we have less than n linearly independent vectors, we don't get the entire space Cn. We'll get something smaller, and it'll still be a subspace, but it won't be the whole entire space. Okay. Now notice that I don't necessarily have n eigenvalues. I put k eigenvalues here. So when would I have n linearly independent vectors? Well, that only happens, remember that our polynomial, our characteristic polynomial, looks like this. And we said that the sum of these mi's, i's 1 to k, is equal to n. And we said that the dimension of each eigenspace is the geometric multiplicity of the eigenvalue lambda I. And we said that the geometric multiplicity is equal to or bigger than 1, and is less than or equal to the algebraic multiplicity, which is these mi's. So we're going to have n linearly independent vectors if the geometric multiplicity is equal to the algebraic multiplicity. If you have just one eigenspace whose geometric multiplicity is less than the algebraic multiplicity, then you won't have n linearly independent vectors for this basis B. So we have to have that the geometric multiplicity is equal to the algebraic multiplicity for all lambda I. Okay, so that's something we have to check. And if that's true though, so we would have that the direct sum of all these eigenspaces is equal to Cn, and that tells us that we can write any vector in Cn as a sum of vectors from these eigenspaces. And that's what I want to do next. So let me give you an example. Okay. So here's an example. And this is actually something we've done. We had this matrix in a previous video, 1, 2, -1, 2, 4, -2, 3, 6, -3. And we said that the characteristic polynomial for this matrix was, I think it was lambda squared, lambda minus 2. And we had that lambda is equal to 0 and lambda is equal to 2. Here the algebraic multiplicity is 2, And for this eigenvalue, the algebraic multiplicity is 1. Again, you can look back over the video if you need to recall all of this stuff, or look back in your notes. We also said that the 0 eigenspace is equal to the span of the vectors -2, 1, 0, 1, 0, 1. So the geometric multiplicity was equal to 2. And we said that for the 2 eigenspace, this is the span of the vector 1, 2, 3. And so the geometric multiplicity is 1 for this one. So if we take E0 and add it to E2, we get the span of these 3 vectors. And you see that these vectors are linearly independent. Remember, their intersection is just the 0 vector. These are linearly independent, and so this one has to be linearly independent from these because the intersection is 0. And we have 3 basis vectors, so we can think of this as a basis for E0 plus E2, but all of these vectors are linearly independent and they belong to C3, which tells us that E0 plus E2 is equal to C3. Okay? Now, if this geometric multiplicity was 1, then we would only have 2 basis vectors, so it couldn't equal C3. So what I want to do is I actually want to write a vector in terms of this basis, and then say, write it as a vector in E0 plus E2. So any vector V in C3 can be written uniquely as V is equal to E0 plus E2, where E0 is just some vector, capital E0, and E2 is just some vector in E2. If you want to label them something different, I just wanted to be able to see that these belong to these particular eigenspaces, but you could call it like R and S, where R is a vector in E0 and S is a vector in E2. I want to show you this. I want to show you how to actually get these vectors. So let's see. We're going to find the coordinate matrix. Let's just do an example. Let's let V be the vector 1, 1, 1. Okay? I want to write it in terms of 2 vectors that belong to E0 and E2. Well, let's write this in terms of the basis that we found. This basis for E0 plus E2. So let's copy this and move it down here. So this is our basis. Right here. So let's find the coordinate matrix that corresponds to this basis. So I want to find the C1, the C2, and the C3, where we can get this 1, 1, 1. So what number do I have to multiply this matrix by, and this matrix by, and this one by to get this particular vector? So how do we do this? Remember that we just need to make an augmented matrix with these as the columns and then 1, 1, 1 here, and then find the reduced row echelon form of this matrix. So you can multiply this row by 2 and add it to the top row. So I'm going to do that, and I'm actually going to write it down here. So 2, 0, 4, 2. Add it to the top row, you get 0, 1, 5, 3. Then I'm going to subtract this row from this one. So I'm going to cross this out and make 0, -1, -3, -1 to get rid of this 1 here. So that becomes 0, 0, 2, 2, 1, 0, 2, 1, 0, 1, 3, 1. And the next step is I want to make this a 1, and then I want to get rid of this 2 and this 3 here. So I can actually just go ahead and divide this by 2. Let's put it in black here, 1. And then I'm going to multiply this row by -2 and subtract it from, add it to this row, and then multiply it by -3 and add it to this row. So what do I get? I get 0, 0, 1, 1, 1, 0, 0, 0, 1, 0. So -2, that becomes a -1. This becomes a -3, so I get -2 here. And then let's just reorganize this matrix. So we get 1, 0, 0, 0, 1, 0, 0, 0, 1. -1, -2, 1. And now I found this corresponds to C1, C2, C3. So let's go back up and plug these values in. So we have C1 is -1, C2, let me write this down over here. C1 is -1, C2 is -2, and C3 is 1. Let's go plug that in. Okay. So right here, we have that C1 was -1, C2 is -2, and C3 was 1. Let's double check this just to make sure we did it correctly. This is 2, -1, 0, plus -2, 0, -2, 1, 2, 3. 2, this cancels, I get a 1 on the top. This becomes a 1, and then this also becomes a 1. So that actually worked, which is great. We can erase this now. So we're almost done. We have found the coordinate matrix. So if we called this basis B hat, then 1, 1, 1, what is that right there? Sorry about that, let me get rid of it. This matrix 1, 1, 1 is equal to, in terms of B hat, this is -1, -2, 1, the coordinate matrix. But what I'm trying to actually do is I want to write this matrix as something from E0 and something from E2. Well, we know that this basis here is the basis for E0, right? Let's scroll back up just to recall that. The basis for E0 are the first two vectors, and this is the basis for E2. So scroll back down. We can say, let's move this over here. These two vectors, actually just erase it. These two vectors belong to E0. This vector belongs to E2. So let's combine these. This is equal to 2 minus 2, which is 0, negative 1 and a 0, and then a negative 2. I'm just adding these two vectors together. And then this vector is 1, 2, 3. Okay. So what we've done is we have written this vector as a vector E0 plus E1, where this belongs to this eigenspace, and this one belongs to that, I think I called this E2. And this one belongs to this eigenspace. And I want to show you something pretty cool, at least I think it's cool. So what can we do with this? Just erase some stuff down here. Let's apply the matrix to this vector. And we're going to see that it's actually just a linear combination of this vector plus a linear combination of this vector. So let's go back up and review what A was actually equal to, the original matrix. This was our matrix. Let's move it down here. Okay. Let's apply this matrix to the vector 1, 1, 1 and see what we get. Well, we get 1 plus 2 minus 1, 2 plus 4 minus 2, 3 plus 6 minus 3, which is equal to, so these cancel, we get 2, 4, 6. Okay, you can see that 1, 1, 1 is not an eigenvector, because if you multiply this by a 2, you'd get 2, 2, 2. If you multiply it by 4, you get 4, 4, 4. There's no way to get 2, 4, 6. So this vector here is not an eigenvector. However, if we apply this matrix to these two, these are eigenvectors. So this is a sum of eigenvectors. So if I put that matrix down here, and then I apply this to 0, negative 1, negative 2, plus 1, 2, 3, right? Well, this right here, we know that this belongs to the 0 eigenspace. So this vector, because it belongs to the 0 eigenspace, is just going to be 0 if I apply this, because this is going to equal, let me show you what I'm going to do here. So this matrix is A. So this is going to be, I don't want to rewrite this, so let's say that this matrix is A. So this is going to be A times 0, negative 1, negative 2, plus A times 1, 2, 3. But this belongs to the 0 eigenspace, so this is 0 times 0, negative 1, negative 2, plus, well, this belongs to the 2 eigenspace, which is 1, 1, 2, 3. And we get 0, 0, 0, plus 2, 4, 6, which is 2, 4, 6, which is what we wanted, this 2, 4, 6, right? So what we've done is we've taken a vector that is not an eigenvector, but we wrote it as a sum of 2 eigenvectors, and we can see that if we apply A to it, we just get the the eigenvalue times this eigenvector plus the eigenvalue 2 times this eigenvector, which is really neat.